Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at the effect of changing of the coefficients, that is molar coefficients, on the heat of reaction. And this is a topic that we're still discussing under the thermochemical equations, which of course is under the larger topic of thermochemistry. So for today we are going to see the effect, as I've said, of the change of coefficients and try to see what kind of effect it's going to have on the heat of reaction. So without further ado, thank you and welcome to the topic. So as I've said, we are still discussing about thermochemical equations, and we said that heat of reaction is associated with molar coefficients of, which is of course thermochemical equations. And now we are going to look at this particular or specific relationship that we are talking about, the association between heat of reaction and the molar coefficients, and try to see what, if there is a change in molar coefficients, what effect will it have on the heat of reaction. So in that case, we are going to demonstrate this using some specific equations. These are two equations which we are going to use and try to see whether or what is the effect of changing that molar coefficient. Now we're going to use the reaction, which is a combustion of the disulfide, that's the carbon disulfide, and see when the products are formed. That's a disulfide undergoing combustion to form two gases, that is sulfur 4 and carbon 4 oxide. So in that case, let's make this one a stoichiometric equation by trying to balance the number of moles of the reacting species and the product species of the reacting and the atoms and the products, of course. So in this case, we have carbon and then we have sulfur. So we have two different species of elements in compounds forms which are reacting. Of course, this is a gas which is a diatomic gas, oxygen. So the number of carbons we have on this side, I'll use this one to demonstrate. We have one carbon, so the carbons are okay. So sulfur, for this case, we have 2 here, and on the product side we have 1, so we shall have to change this one to 2 for us to balance the sulfur. So that one definitely affects the number of oxygen atoms on the product side. So the number of oxygen in this particular case, the reacting side, is 2, and this one is 2 plus 4, which is 6. So we shall have to put a coefficient of, that is 3 there, to balance the number of oxygen on the reacting side. So in that case, this one, as I have said, we do not indicate, but in any case we can just put that it has no effect. So when it is just like this, it indicates that the coefficient is 1. So I can see that the elements or the number of moles of the reactants and the product side are balancing for the respective reacting species and the product. So in that case, it's good for us to also indicate the state of this reacting species and the product. As we said, this is very important because it does a direct relationship to the heat of reaction that we are talking about. So this one is a liquid disulfide that is reacting with oxygen or undergoing combustion in air to form carbon 4 and sulfur 4 oxide respectively. So in this case, the heat of reaction, change in enthalpy, heat is evolved, as we said, using the negative sign implies that heat is evolved, which is 1075, that is kilojoules. And then suppose we have So in this case, we can do a reaction under maybe full or limited supply of air, as in the case of carbon 2 and carbon 4 oxide. So in this case, suppose we have a different ratio of the coefficients that we are talking about, then we shall still have the equation as it is, which is the disulfide plus oxygen gas undergoing combustion to form carbon 4 plus sulfur 4 oxide. And then suppose, these reacting mole ratios are the same as volume, so suppose we have a volume of the disulfide, and then this is half still 3.5, or 1.5 is equivalent to half of that. And then for carbon 4 oxide, the product that will be formed will be half and 1 volume of sulfur. So still we shall have the phase of those reacting species and products just the same as they were, because these are gas, and we form two gases. So in this case, we see that the reacting volumes and the products which are formed are half of the first equation's coefficients. This is equation number 1 and 2. So in that case, it will be observed that whenever these kind of coefficients are affected maybe by a half, this one changes the value of the heat of reaction also accordingly. So accordingly means that it changes with respect to that particular ratio. So in this case, our heat that is evolved will also change by the factor of half, which is 537.5 kilojoules. So which means dividing the reacting and product coefficient by half also results in half of the heat of the reaction that is involved. Therefore, from this particular kind of concept, we can deduce that in a chemical reaction, which is of course a thermochemical equation, if we are able to divide or multiply, this one has been divided by 2. If we are able to divide or multiply the coefficients by n factor, the heat of reaction of the new equation will also be obtained by dividing and multiplying that amount of heat, which is a heat of reaction, by the same factor. So we have divided the coefficients by half. Similarly, then we shall have to divide the heat of reaction that is involved by the same factor. So that's basically a rule that applies in thermochemical equations. So suppose there are some reactions which of course involve reaction forward and reverse reactions, which means maybe they are reversible. Now what happens to those cases of reactions which of course are reversible? Like the first change of course liquid water that we said can be able to change to gaseous states, like the equation that we had given. And there is another one that can be able to change from liquids to gases. So in these two phases, you will find that if the heat was evolved in the first instance of forming a reaction, and then taking a reverse of that particular reaction will accompany absorption of heat. So let's give one example of what we have talked. Suppose we have oxygen reacting with hydrogen gas to form liquid water. The heat of reaction in this case, which is change delta H, it will evolve 571.7 kilojoules of heat. That's when, of course, we have to balance that equation. Now, suppose we have the product as a reactant, then we shall have liquid water forming its products, which are the reactants from this first equation. which is 2 hydrogens plus oxygen. Now in that case we shall have the change in heat, which is the heat of reaction, change in enthalpy, which is positive 571.7 kilojoules. So as we can note, there is a characteristic change in equation 2 from 1, whereby if we reverse the equation, that is, if we reverse the equation 1, there's a characteristic change of the signs that we are talking about, which implies exothermic and endothermic reactions, whereby in the first scenario, heat is taken from the system, and in the second scenario, heat is absorbed into the system. So therefore, for that case, we shall have a rule that applies for these particular two scenarios that we have talked about, whereby when a thermochemical equation is reversed, the value of the heat of reaction, which is change in delta H, reverses the sign that we are talking about here, which implies either the endothermic or exothermic reaction. So as we saw in the first case, that if the coefficients are affected by half, then the heat of reaction also changes by half accordingly. In the second scenario, we have said that reversing the equation reverses the signs of the heat which are accompanying the values there. So maybe for an exothermic reaction, reversing the sign means it's going to be endothermic. Now in that case, we're going to see that this rules also will apply for maybe changing the value of the coefficients, and the products will affect the change in heat, the change in enthalpy respectively. Now what happens to the mass and the number of moles? As we said that we have tried to see the effect of change of coefficients on heat, and as well we can see the reverse of changing of heat on the mole ratios which are reacting. Let's try to see the reverse of that. Of course, we have seen the effect of coefficients on heat and the effects of reversing the equation on heat. Let's try to see the effect, of course, of trying to change the amount of heat on the molar coefficients. So suppose we have an equation of combustion of a hydrocarbon, which is propane. Combustion of propane to form, of course, hydrocarbons burn to form CO2 plus water. So let's try to balance that equation. Of course, this is a propane gas, hydrogen oxygen gas, CO2 gas, and this is steam. So in that case, let's try to balance the reacting and the product side for the coefficients. We shall have 3 carbons on the reactant side, so we change this one to 3 in order to balance the number of carbons. So that one will in effect change the number of oxygen on the product side. So we shall have 6 plus 1, that is 7. Let's try to make it an even number because they react in full ratios. So let's try to see by adding 2 there. So we have 6 plus 2 forming 8. So we shall add 4 on the reacting side to try and see whether we are able to balance that. So we have 8 oxygen, 8. And then the number of hydrogen there are 4. So this one will force us from the side of the propane to change this one so that we can balance the number of oxygen. So for that case, we shall have 4 on that side, N3. So for this case, we have hydrogen balancing. So oxygen, this is 3 plus, this is 6 plus 4, which is 10. So we have 5 on the reacting side. So in that case, I think that equation is balanced. And now the heat that is evolved from that kind of reaction, as an exothermic kind of reaction, we shall have change in enthalpy is equals to negative. This is 2044 joules, kilojoules, 2044 kilojoules, or 2044 kilojoules to form those particular products. That's a combustion process. So suppose we are asked what amount of propane gas will be required to produce 255 kilojoules of heat. So what if this reacting species produces 2044 kilojoules of heat? What amount of gas will be required to produce 255 kilojoules of heat? So in this case, since we know that the coefficients possess a proportionality with the heat evolved, then we'll have to compare the ratio of the heat, the reacting mole species. So in that case, we are being required to find the mass of propane required to produce that amount of heat. So if the mass is proportional to the reacting volumes, then it will be in order for us to conclude that the reacting volumes for this particular case for propane is 1 mole reacting with the oxygen 5 volumes to form those products. So 1 mole is able to produce, 1 mole of propane burning is able to produce that amount of heat. So we shall have to compare that proportion. So this one I can do away with this since we have already taken the ratio for the reacting moles. So if 1 mole of propane produces 2044 minus, this is kilojoules of heat, so that is the heat of reaction. How many number of moles will produce negative 255 kilojoules of heat? So that one actually we shall do cross check, but since we are required to find the mass, we can be able to convert this 1 mole of propane into mass. Since the molecular formula for this kind of gas is C3H8, we just add the masses of the respective elements which are forming that compound, and then we shall find this carbon, that's a molar mass of 12. So 3 into 12, because we have 3 carbons, plus 8 into 1. Hydrogen has got a mass of 1, that is 1 mole. So we shall have 44 grams per mole of propane. This is C3H8. So 44 grams are reacting to form this. What is the amount in grams reacting to produce that amount of heat? So this one we shall just get it as 44 grams. So we are after finding the mass that is reacting to form this amount of heat. So for this case, we shall do a cross multiplication for us to find that. So we shall write 44 grams, that is per mole, times 2, that is minus 255 kilojoules, divided by, this is 2044 minus kilojoules, this is kilojoules per mole. So this one will cancel, is of course the units, and this one will go with this. So the amount that we're going to find is in form of grams, and this one will give us 5.48, which is equivalent to 5.5 grams of propane required to produce a change in enthalpy that is equivalent to negative 255 kilojoules. So in that case, the relationship between the relationship between the coefficients on the reacting and the product side is directly proportional to the change in heat. So those two concepts are going to assist us try to find the relationship between mass and the reacting species. So in that case, we come to the final step of our discussions of the concepts which are applied in thermochemistry. There are others like the heat capacity that we're going to learn after this, but of course they'll be forming a conclusive part of the entire topic that we are going to discuss in thermochemistry. So for that case, thank you very much guys for today. Bye, God bless you.